Good afternoon, good evening, good morning to those who are listening to this webinar. First of all, I'd like to thank Park Systems for this opportunity to deliver content to you. And I'm a professor at Case Western Reserve University, Department of Macromolecular Science Engineering, and also a member of the CLIPS STC and director of PetroCase. So let me start by introducing our topic today, smart fluids and gels. We're going to talk about different stimuli-responsive fluids, gels, a little basics about rheology, different applications. In particular, I'm going to focus one section on the oil and gas industry. But in general, smart fluids and gels refer to different types of liquids, gels, viscoelastic fluids that have very interesting properties other than your normal classification of Newtonian and non-Newtonian liquids. So first of all, Case Western Reserve University, we are located in Cleveland, Ohio. This is a pretty part of Cleveland. The area is called University Circle, home to Cleveland Orchestra, Cleveland Clinic, Cleveland Museum of Art, and of course Case Western Reserve University. So if you happen to be in the area, let me know. Also, it's a comprehensive university. We have our share of famous alumni, including Nobel laureates and the founder of Dow Chemical Company. We are located at the Macromolecular Science Engineering Department building called Kent Hill Smith, and my lab is at the 5th floor. Also, I want to let you know about our innovation center called ThinkBox. We have a lot of activity involving additive manufacturing and 3D printing. And this facility is open for business, both for industry and academic partners. But primarily, the institute is geared for accessibility, especially Case Western Reserve University students. And then lastly, PetroCase is a center that I started dealing with the high demanding needs of the oil and gas industry, from high performance materials to coatings, fluids, different types of completion, drilling, and production or extracting chemicals and materials. So for example, you see in this picture, we work on coatings that are super hydrophobic, different fluids that control emulsion stability, as well as propans used for hydraulic fracturing. So if you have any questions, by the way, you can email me at rca41@case.edu. So we are an academic group after all, and I lead a group of about 8 PhD students and a couple of master students. We work a lot on nanomaterials, nanostructured polymers, investigative methods at the air-water interface, or a variety of surface chemical modifications. So we have done a lot in this area. On the other hand, we are also doing research related to industry. So our laboratory, just to give you a picture here, is comprised of a section devoted to material synthesis, as well as characterization of surface properties, bulk properties, and even rheological properties. On the other hand, we built a number of capabilities related to the oil and gas industry and research, which deals with investigating fluids, different types of hydraulic fracturing, fluid compositions, flow assurance, corrosion problems, brine fluids, and testing of propans, as well as other chemical inhibitors. So as an outline, we're going to talk about some basics of rheology, just to put the context of viscoelastic fluids, talk about gelation phenomena. I'll outline to you several examples of smart fluids with stimuli response based on physical and chemical cues, as well as some applications for the oil and gas industry. And I'll close with some examples of how AFM is related to analyzing gels. So for example, smart fluids really involve that of stimuli responsiveness. That stimuli can result in a change in flow conditions, viscoelastic properties, different types of response in the presence of light, temperature, pH, magnetic field, electric field. So for example, we can talk about emulsions or microemulsions. Fluids can also be classified as equilibrium or colloidal dispersions. So different types of fluid compositions are utilized for the applications involving not only the oil and gas industry, of course, but many things from lubricants to hydraulic fluids, different types of investigative methods, as well as biomedical applications. So some basics here. Rheology is basically a study of the manner by which materials form, deform, flow. The mechanical constitutive relationship can be broken down basically to looking at the elastic response, which is the modulus, or the viscous response, which is the viscosity. And this can be modeled by the application of force as exhibited by a stress-strain relationship, which of course gives you the modulus of any material. Here we can consider, though, the application of shear flows or stresses that will be experienced in the presence of a fluid versus that of a solid-state material that is being deformed. So we can say that rheology applies to fluids, melts, gels, when we are interested in deformation behavior or flow behavior. This can also be classified as an affine deformation or non-affine deformation. That is the distinguishing mark is that of a linear to nonlinear response. In a uniform deformation where you have local strain equal to macroscopic strain, it's classified as affine deformation. On the other hand, non-affine deformation results in significant changes in rheological properties over time or other types of field effects. And this is exhibited, for example, by non-Newtonian behavior in biopolymers, gels, emulsions, and other types of suspension. Perhaps you're more familiar with liquid behavior being classified as Newtonian or non-Newtonian. In a Newtonian behavior, you have a shear stress response to shear strain rate defined by a straight line or a linear relationship. On the other hand, one can classify shear thinning and shear thickening based on changes in the viscosity with the strain rate. So for example, a decrease in viscosity at high shear rates is classified as shear thinning, and an increase in viscosity with strain rate is classified as shear thickening. The non-Newtonian behavior can also be observed in terms of this view graph here. Again, as a stress-strain relationship, a Newtonian would be a linear response, but pseudoplastic is another term for shear thinning, is exhibited by pain, or shear thickening behavior, a dilatant behavior, for example, water plus cornstarch, plastic deformation, and a Bingham-Newtonian behavior such as ketchup. And there are other terms like thixotropic, Bingham or Bingham plus constant viscosity behavior and so on that we can classify. Now, key to measuring viscosity as well as rheological properties is the application of a viscometer, or more in the research mode involving that of a rheometer. A rheometer can be stress controlled, where you can investigate the frequency, the complex components, including the G prime, G double prime, extensional rheometry, and so on. And I'm not endorsing any particular instrument, except that some of these instruments I've used and are available at Case Western Reserve University. And of course, different types of measurements set up from a rotating cone to other types of methods that involve application of shear stress in the presence of temperature or even high pressure. So why are we interested with this? A good example is the amount of study involved in the oil and gas industry when it comes to fluids. So a good example here are drilling fluids, which can be based on water, oil, synthetic, or emulsion. That means that these drilling fluids, one needs to investigate their thixotropic behavior in the presence of other additives, weighting agents, different types of fracture stabilizing agents, etc., including clays. Then one needs to, in particular, study their behavior with respect to pressure pumping, shear rates, and also depth. As you go to deeper formations, for example, they experience high temperatures and so on. So you can imagine that the oil and gas industry, in particular the upstream and exploration, deals a lot with properties of highly designed fluids for drilling. And so rheology is a very important factor, as well as smart fluids. Now we can also introduce to you gelation at this point. Gelation is spanning that of a solid-like property to that of a transition into from gel to a viscous to an elastic response. Gelation is a phenomena where you can associate with cross-linking, complexation. Therefore, you have differentiation between a physical and a chemical type of gelation. If you have more components than one, or the presence of solid particles, this can be heterogeneous, different length scales, both short range and long range ordering. So the next time you eat a punch salad with gelatin, remember that there's a lot of science that can go to understanding that delicious dessert, from the formation of stable collagen network to its breaking down of this gelation behavior due to reordering of the hydrogen bonding forces between this protein and the presence of breakdown systems based on enzymatic hydrolysis. Okay. Another thing you can associate with fluids is, of course, the sol-gel process. The sol-gel process allows you to look at the formation of homogeneous to heterogeneous systems and the incorporation of cross-linking, for example, as it relates to the formation of glasses. So when we say solvent-base, this will form into powders or serogel films, forming a dense ceramic film. Basically, it doesn't go through a gelation state, and it involves a simple removal of the solvent or evaporation. On the other hand, a gel phase would involve networking, where one can distinguish here a direct solvent evaporation resulting in a serogel, or removal of the solvent through pressure and, let's say, supercritical extraction, freezing the network structure resulting in an aerogel. The sol-gel, fluids, gelation are related. Another is we can classify gels based on a reversible or irreversible phenomena. Reversible would indicate a physical cross-linking. On the other hand, irreversible would involve the formation of, let's say, covalent bonds or condensation or chemical reactions, as in the case of this example. So reversible, irreversible, or physical and chemical. So what happens with gelation is you come to a point where you have a transition of infinite clusters to that of a networking structure. That means gelation can be described by a bond percolation transition, where essentially the components or the particles or the bonds are immobilized in a mobile matrix or solvent. Probably this is more meaningful in showing that from rheology, one can understand its relationship to mechanical properties by the transition from a viscous response to an elastic response. So viscous response will come from the liquid side. A Newtonian liquid, for example, at the beginning with increasing viscosity, will come to a point that a modulus is developed, indicating that it has transitioned to an elastic towards a solid state response as a network is developed. So one can think in particular of how thermosets or epoxies are formed, starting from a viscous to a elastic response as the epoxy glue or adhesive hardens. In another case, a simple test would simply be looking at the gel point. The gel point is the state by which gelation results in an increase in shear modulus, and therefore a gel state will have very much reduced flow properties. Let's say in the case of a gel that is formed on a test tube and you turn it upside down. Here you can see chemically what's happening with a cross-linking process forming a hardened thermoset resin such as an epoxy. An epoxy is a two-component part A and B system involving that of the epoxy precursors, and when you mix in the hardener, which is typically a diamine, resulting in this network structure, covalently link groups of an epoxy resin form or reform in the presence of an amine. So thermosets actually are an extension of the gel effect. The thermoset is a term which means that the material or the polymer, once it's formed, cannot be thermally deformed as compared to a thermoplastic. So in a thermoset, basically you have this network structure. The more connected it is, the higher the modulus. In other words, gelation, for example, starts with very few connections, and thus, as all of the connecting points are consumed, you have thermoset or hardening that can be measured by a change in modulus. So chemical cross-linking involves the following. As simple as taking polyvinyl alcohol or any polymer that contains a hydroxyl group such as guar or other types of polysaccharides. One can utilize glutaraldehyde to affect the formation of a cross-linked network. And this can be activated in the presence of acid. So essentially, you want to term glutaraldehyde as a cross-linker for polysaccharides. And indeed, that is being used in some application. Another involves the formation of radical species. Let's say the chemical or irradiation treatment of a polymer, generating radicals with functional monomers that are reactive. That means that these radicals need to pair up with other radicals, stabilize, and form graphs or cross-links through a radical cross-coupling reaction. Physical gels are characterized by changes in pH or the presence or absence of ions and things that involve hydrogen bonding, helix formation, entanglement, microphase separation. All of this can be reversed by either removing the stimuli or the addition of screening agents. So for example, various types of physical crosslinks can be found between PVC and a plasticizer or between a dry block of polymer in the presence of water or even complexation of PMMA and isotoxic PMMA in toluene. So in a thermoreversible gelation, one can reverse this transition behavior by going from cross-link to a disentanglement, from phase-separated to miscible systems. Again, this is involved both in synthetic and even biological phenomena. So like what I described earlier in the case of gelatin, a main ingredient is a polypeptide or protein carrageenan. And in the presence of heat or upon cooling, it forms the helical links that complexes this biopolymer, and one can, of course, increase this aggregation of the helices in the presence of salt. So, for example, salt and heat is intimately connected with gelation of carrageenan. As you can see here, the ionic interaction can be observed more prominently in the presence of divalent metal ions. So salts, in fact, are very much used in the oil and gas industry as methods of controlling viscosity of fluids. A hydraulic fracturing fluid actually is a gel that is used for the completion phase in improving productivity in tight shell formation. One of the ways that these gels are broken down, let's say, could be controlling that the salt concentration or by the use of gel breakers based on radical reactions. So as the gel, for example, goes to different types of formation, it encounters different levels of brine conditions, and that can affect the viscosity. Simply, as you can see here, the stabilization in the presence of salt can control some of this interaction present, let's say, in santan gum or guar. Here, you see a different type of phenomena based on coacervation. Coacervation basically is complexation of oppositely charged ionic species. So, for example, an anionic polymer and cationic polymer can coacervate or complex and precipitate. And thus, you will find this type of work in both sedimentation and flocculation phenomena in other types of fluids. Another is hydrogen bonding. So clearly, hydrogen bonding in the presence of a weak polyelectrolyte such as polyacylic acid or sodium salts of carboxymethylcellulose derivative. So the carboxylic acid can interact with each other in the presence of salts, but in the change of the pH, it renders it negatively charged ionic, or in the presence of, let's say, another polymer with an opposite charge, a polycation, you will have coacervation. So in that case, it ranges really in terms of hydrogen bonding to ionic interaction in the case of weak polyelectrolytes. Another is you can have the aggregation based on a separation in solubility and complexation between, let's say, a polypeptide or a polysaccharide component. This is the case of, let's say, a biomaterial or a natural material source such as gum arabic, where you have the proteinaceous part of the molecule leading to a cross-linked hydrogel network. Okay, so I think at this point we are ready to look at smart gels and liquids. So in all of these examples that I'll be showing to you, basically what we need to understand is the relationship of the response with the stimuli that is applied and the type of flow behavior or restriction that can be observed with the application of that stimuli. So one example here is a response or a mechano-responsive gel that affects the photonic band gap of lamellar bilayers of a polymer hydrogel, which changes not only its mechanical response but its optical properties. So for example, here a band gap basically is composed of a periodic structure with different refractive indices, and in the presence of a stimuli, this changes from an unswollen to a swollen state. That is seen as a change in the optical response, as you can see here with the shifting of the color, giving you that change in band gap. On the other hand, you can see the change in mechanical response by the stretching of the gel from the original state. So you can see here a mechano-responsive gel that's also visible because of its band gap structure. A chemoresponsive gel means that you have a chemical stimuli added or withheld that changes its gelation or flow behavior. As in the case of this polyoxyethylene glycol with dopamine groups and alanine interacting at the end groups, you will have a gelation effect where this gel was actually formed on a material. Now, material substrate. Now, this one in particular, I think I forgot to give the exact reference here, is used for tissue engineering. What happens is in the presence of an elastase enzyme, this elastase enzyme will decouple or break this interaction with the PEO, thus resulting in the breakdown of the gels. In other words, the presence of an elastase enzyme will reduce the viscosity of this gel that is formed with the tissue, and hence it might affect its ability for tissue engineering integration. Here, we have a pH-responsive gel. As I mentioned earlier, the presence of divalent salts with polysaccharides tends to increase its viscosity, and as in this case, the polyelectrolyte membrane switches between that of a closed to open state. And here is an example or an effective use of AFM to look at the change in morphology with pH response. So the corresponding change in viscosity can also be tracked by a change in the morphology as observed by AFM. Here we have a heat-responsive gel. Basically, these are objects that are formed utilizing a what we call temperature-responsive polymer, such as polynipam or poly-N-isopropyl acrylamide. This polymer nipam has an LCST or lower critical solution temperature, something in the range of about 34 degrees Celsius. So what happens is as you change the temperature, actually the gel goes to a more hydrophobic state and it collapses and becomes more rigid. On the other hand, by cooling it below 35 degrees or the LCST, it lowers its viscosity and has more of a gel response. So in that case, by transitioning with temperature between 35 below and above, you get these particular changes in the shape or have a shape memory effect on the gel. Photorheological fluid is exemplified by this change in the flow properties of a C-tab surfactant containing a cinnamate acid derivative. In this case, the transition from a trans to a cis results in the breakdown of that long-range interaction or morphology from long worms to short cylinders. Thus, it results in the breakdown of the gel properties towards that of a more viscous fluid. Yet another example is that of a photoacid generation, changing the ability of a pluronic surfactant such as PEO, PPO, PEO that's originally absorbed on the surface of clay. And this interaction means that the surfactant is not free it's not free or is absorbed on the surface. Hence, the clays are prevented from interacting electrostatically with each other. On the other hand, by the presence of the photoacid generation, acid groups are developed, which in turn changes the ability of these pluronic surfactants to absorb on the surface, as well as changing the charge density on the clay. The result is you get a more gel-like behavior in the presence of the acid that was generated by UV light. So this is a photoacid generation event, and this is irreversible. Here you have a photorheological fluid based on, again, a cis and trans differentiation of this azobenzene group plus surfactant. So this particular complex or vesicle forms originally a worm-like structure. On the other hand, in the transition from a cis to a trans state, you break down this worm-like behavior, again producing a more spherical vesicle, and hence a dramatic change in viscosity. Here again, another example of a photoacid generated effect. The photoacid generation, once photolyzed, releases the protons. In this case, you have gelation based on the ability of the calcium to be neutralized into calcium cation, calcium carbonate to calcium cations, hence facilitating the interaction between that of the protein double helix constituents. The protein here is either alginate polysaccharide, alginate, or pectin. And here you can see the change in viscosity dramatically before and after UV irradiation. Yet another example is that of a spiropyran photoactive group. The spiropyran is hydrophobic, and after UV irradiation it becomes hydrophilic or charged in the presence again of your surfactant. So here you have a vesicle slash worm-like transition. So irradiation results in a change from a worm-like to a vesicle type of interaction, and in fact this is irreversible. This is reversible. Okay, and here I'll skip this example. We showed it earlier. Here you can see the rheological measurements that distinguish the G prime and G double prime as a differentiation between the gel and non-gel state. Here it's an example of a hydrophobic to hydrophilic association. A polymer such as the material shown here is called an HEUR. It's an associating polymer where you have by design a PO backbone, a urethane spacer, and a hydrophobe at the end group. The hydrophobe basically interacts with the cyclodextrin in a guest-host interaction. The cyclodextrin is a poly or oligosaccharide that has an internal hydrophobic structure. So schematically what happens is as you mix these two together, you will have the end groups being capped by the cyclodextrin, and upon heating, this interaction is minimized such that the hydrophobes are able to associate. So that means heat increases the viscosity, as shown here. Different types of the host cyclodextrin induces different types of viscosity behavior as a function of temperature. Or one can say that there has to be an exact size of the cyclodextrin in order to be more effective in displaying that rheological transition. Here, in a two-phase fluid, you have the surfactant and their worm-like or vesicle behavior, being able to separate that water and oil phase. So basically a gel is formed with the oil, but in the presence of ethanol, it breaks down this association such that you revert back to a thin liquid. So the gelled oil and water can be used for phase separating systems and its combination towards a more homogeneous gel composition. So that means gel states can trap basically oil, kerosene, and other hydrocarbons, whereas the surfactants can keep it separated from the water and a gel phase or make a more homogeneous phase. At the beginning, I showed you some magneto and electrorheological fluid examples. So any suspended material that, let's say, is present on the liquid in response to the presence of an electric field or magnetic field can change its flow properties. So in a suspension type electrorheological fluid, let's say oil and matrix and a particle, essentially you control the aggregation states of the particle, and you will control the flow behavior. In a blended type ER fluid, you have oil plus other polymeric materials, including liquid crystal. On the other hand, a homogeneous type electrorheological fluid, let's say, will have a ferroelectric polymer that is present. So the change in viscosity essentially results from a change in response of these particles or polymer present in the application of a voltage, and thus you can control the flow behavior with the electrical response. So for example, here you can see a suspension type ER fluid. The particles in the presence of a field, electric field, induces shear stress. In a blended type ER fluid with liquid crystalline groups, again, the shear stress is present in the presence of an applied electric field. So electrorheological fluids in the presence of, let's say, a PMMA polyaniline composition results in a change in the interaction of the surfactants with respect to the presence of a polymer. Now, this conducting polymer makes it responsive in the presence of an electric field, as shown here. So the control of the stress behavior is a response to the alignment of the particles with an electric field. Here, you can see different voltages controlling the rheological or shear stress behavior. Magnetorheological fluid means that you have magnetic agents or particles present, and the alignment of a magnetic field changes that of the flow behavior simply because the particles are aligned in an anisotropic direction. Magnetorheological fluids actually are very important in some type of applications, including suspension dampers or transmission clutches or certain types of sensors. And this fluid response is highly specialized, and in the presence of an electromagnetic field can be made anisotropic to give you that anisotropic response, let's say in a turn on and turn off type of application. There's interest in, let's say, using magnetorheological fluids for improving drilling fluid properties, perhaps by improving the mud displacement. This can be done by controlling the thixotropic behavior. Magnetic fields are increased as you go down deep into the formation, or electrical fields can be created artificially with wire lines, and there's some interest on utilizing magnetorheological fluids in drilling fluids, and that is not remote because magnetorheological fluids can easily be done by using magnetite and other type of iron additives. Okay, so these iron particles shown here mixed with clay and a surfactant, and essentially as you increase the concentration, you can see this effect or magnified effect as a function of concentration or even depth on drilling. Here are some of the possible applications of the smart fluids. For example, smart fluids containing multifunctional nanoparticles can result in improved circulation as well as preventing formation damage. Smart fluids can reduce the torque and drag in the drilling process. Essentially, there's a lot of pressure control needed, pressure pumping as well, rates that needs to be controlled in order to make an effective or cost-effective drilling performance. Another is that of lubricating properties. So, for example, different types of formation damage can also result in particles that actually are degrading to the tools, drilling tools that are utilized in drilling. I'll be closing with some examples of how AFM has been used for imaging and investigation of gels. Primarily, one can look at the vesicles and worm-like structures or lamellar phases as the surfactants, gelating material, or increasing viscosity goes from high viscosity to low viscosity as these network structures, for example, are broken down. So, for example, peptide-based hydrogels change in viscosity. as well as the presence of, again, I showed earlier the presence of surfactants. And then once you deposit these vesicles or lamellar structures on surfaces such as mica, one can use AFM to distinguish the network or broken network structure. Here is an example of an oligothiophene polymer, which is actually a conducting polymer. In this case, it also forms long-range anisotropic structures that are extended in fibrous form here as a function of, let's say, concentration, range, and concentration and resolution. Here's an example of how a technique called force clamp force mapping was utilized to look at the performance of a polyacrylamide gel and its use for tissue engineering. So in this case, the contact height, the scaling parameters can be observed simply by the interaction of a AFM tip or the cantilever to the gel or the cell. So it's a force clamp measurement, basically looking at the strength or weakness of this interaction. At any rate, I'm ready to close, and that's about it. So I'd be happy to answer any questions you may have. Thank you.